In the last lecture, we learned that if we add small impurities to pure semiconductors, they become extrinsic semiconductors. That means, they become better conductors. If we add trivalent impurity, we get what is known as p type semiconductor. If we add pentavalent impurity, we get what is known as n type semiconductor. And then we also saw the properties of p-n junction, and we also learned about the forward and reverse biasing. In forward bias, the lot of current flows and the resistance is very low of the p-n junction. In the reverse bias, there is hardly any current flowing, and therefore, the junction offers a very high resistance. That is what we did last time. Now, we shall continue with the properties of this p-n junction. Remember that if this is positive, this is negative, say on the n side, then it is forward biasing and the current flows. As soon as the polarity changes, the current does not flow. This is called unidirectional property of the p-n junction. The property of the p-n junction diode, that it allows current only in one direction, makes it suitable for use in converting alternating AC voltage into direct DC voltage. In AC, there is a change in polarity every half cycle, and therefore, the p-n junction will conduct when it is positive half and will not conduct when it is negative half, and therefore, we have only the positive voltage, and this process is called rectification, and the device is called a rectifier. A simple rectifier circuit is shown in the next slide. The signal supplies an alternating voltage. During the positive half of the signal, the current can flow through the diode. During the negative half of the cycle, the current is not allowed. During this half, the output is 0. Here, you see, remember the symbol of a p-n diode. This allows current through only during the positive half, and during the negative half, this one is cut off. So, you output is this 0, this positive half cycle 0, and then again positive half cycle. Negative half cycle is cut out because there is no current through this p-n diode because of this becoming negative. When it is negative, there is no current flowing through the junction, and therefore, the input signal is like this. In the output signal, this one is removed. We have this 0, this. This is called half wave rectifier. Why? Because only half, this one is rectified, this one is rectified, but this one is not. So, it is half wave rectifier. The output is like this 0, again like this, half positive cycle, 0 positive cycle, that is the output, and we can calculate the average in terms of V max. The average would be 1 by 2 pi 0 to pi sin x dx from 0 to pi only, and this value is 0.318. So, therefore, the average value of the rectified voltage, first of all, rectified voltage is only in the positive direction. So, it appears as AC, and the average value is 0.318 V max, and since V max is root 2 times the RMS value, therefore, it is 0.45 times V RMS. However, the output voltage is not steady, it is not DC. You see, you can this like this like this, it is not DC. To make it steady, we have to use a filter, especially a capacitor. How does the capacitor work? Recall charging of a capacitor and discharging of a capacitor. The charging is that it accumulates charge on the capacitor, the charge is accumulated on the capacitor. On this side, the charge is being lost from the capacitor. This is discharging, this is charging, and discharging, this depends upon the size of the magnitude of the capacitor. So, as the output voltage increases to V max, as the output voltage increases, there is charging, and when it reaches the maximum, then there is a capacitor gets charged, then it gets discharged till the meet the next positive half cycle. Let us explain with the diagram. You see, this is the input and output is like this. You see, this is the capacitor is discharging. When it meets this hump, this starts charging because there is a positive potential, and when it reaches this, then it goes to this again, starts discharging, reaches this, charges again, discharges again. So, you can see that if there is a capacitor used in the output circuit, then we get this kind of output, this blue one, not the red one, we get the blue one. But this is still not DC, there is there is a variation, and this variation is called ripple factor. We shall come to that in a moment. So, once again to repeat, this is input, this is output. Without the filter, the output was like this and 0 volts. With the filter, with the capacitor in the output circuit, the capacitor gets charged, discharges, gets charged, discharges. So, the charging discharging of capacitor gives us this curve, and this rectified voltage or filtered now voltage is like this, but it is still not steady, it is still not DC. There is a ripple factor here. It still has a ripple, a varying or AC component of frequency equal to the frequency of the input. You see, frequency of this is equal to the frequency of the input, and therefore, there is still this ripple factor of the order of the frequency which is equal to the frequency of the input. What do you do if you want a better output? Then what we do is to rectify this portion as well as this portion. This is called a full wave rectifier, and the circuit is here. You see, we have two diodes and there is a center tap here, and this signal, when it becomes positive, this one conducts, when it becomes negative, this one conducts. So, we have output during the positive half, we have also have output during the negative half. So, we have an output like this. All this negative half has also been made positive half. So, we have output like this. In the half wave rectifier, this was missing. In the full wave rectifier, we have output like this, that all this negative one also has been rectified to become positive, and the average now would be twice that in the earlier case. The earlier the average was how much, 0.318. Now, because we have now all the halves there, the average becomes twice, and therefore, it is 0.637 V max or 0.90 V RMS. Now, if we put a capacitor in the output circuit, then what happens? There is there is the filtering process, and filtering process, the capacitor gets charged up to this, then discharges, charges, then discharges, charges, and like that. So, the frequency of the ripple factor now is twice the frequency of the input signal. One thing. Second, rectification is much better. You can see that you can compare with the rectification, I will show you in a moment. Here the rectification was like this, you can see, and here the rectification is like this. So, rectification is much better, the average voltage is much higher, and this is the process of full wave rectification. The circuit is here, it is called center tap full wave rectifier. In the positive half, this works, in the negative half, this is higher than the center tap, and therefore, this works, and therefore, we have output like this. And then if there is a capacitor in the output circuit, then filtration process also takes place. This is the circuit again for half wave rectifier, only one diode used here, and full wave rectifier, two diodes used here. This diode works in the positive half, this diode works when the polarity reverses, and we have output signal like this. The other uses of p-n junction diode, apart from rectification, include detection of radio signals, which is again in fact rectification, protection against over voltage and switching. We shall see if we have time of these functions. It can also be used as a temperature measuring device and as a variable capacitor. The diodes are the building blocks of logic gates. Solar cells, light emitting diodes, voltage regulator, regulating Zener diodes are all variants of the basic p-n junction diode. No wonder that the junction diode is an important component of all integrated circuits, because there are so many things to be done, and therefore, they are to be used in all integrated circuits. Recall the I V characteristics of a p-n junction: current, voltage. You see that I showed you earlier also. As soon as the voltage is beyond 0.6, there is in silicon diode, the current shoots up, and there is very little reverse current. There is a small current when the junction is reverse biased on this side. It is possible to tweak the structure of the p-n junction, so that at a certain predetermined reverse voltage, there is a breakdown in the depletion layer of the junction and a current starts flowing through the junction. When this is not done, the current is very small, but you can structure the diode in such a way that at a certain potential difference, at a certain potential, there is a breakdown in the depletion layer and the current starts flowing. This you can do, and this, where this is done, in the device in which this is done, is known as a Zener diode. The breakdown is called an avalanche breakdown, because there is a huge number of electrons that start flowing, therefore, it is called an avalanche breakdown. The voltage at which the breakdown occurs is called the breakdown voltage. The flow of reverse current does not allow reverse voltage to go beyond the breakdown voltage. You see, this is the reverse voltage. Up to here it was very small, and at a certain voltage called Zener voltage, there is huge current that flows through the diode, and therefore, the voltage does not go beyond this predetermined Zener voltage. That is why the Zener voltage is used as a rectifier, that is regulating circuit using Zener diode. It is called a voltage regulator. You see, this is a voltage, this part goes through the diode, and therefore, like this is the Zener voltage, and beyond this it does not increase. So, this regulates, the Zener diode regulates this voltage to this. We get constant voltage across the Zener diode of this value V out. The rest of course falls across this resistor. This is a symbol of the Zener diode. So, what is happening, that in the reverse direction we structure the diode in such a way that at a certain predetermined voltage, we can make it anything. We can desire how much voltage we want the output from the Zener. We can decide beforehand, and therefore, we can make the Zener accordingly. And then at this Zener voltage, there is a huge current that flows through the diode, and the voltage does not go beyond this Zener voltage. So, Zener voltage is the regulated voltage, as in this case. This voltage is regulated, it is constant, and the rest of the voltage from this input falls on the resistor. So, Zener therefore, is used as a voltage regulator, is a very important function that a diode can perform. Regulation of voltage, the voltage is regulated, it becomes constant when it goes across the Zener diode. And as I said, we can, any desired voltage we can have where the breakdown takes place, so that the voltage does not go beyond that. This we can determine, and therefore, the voltage regulator, the Zener can regulate voltage, I mean from I think a fraction of a voltage to hundreds of volts. In most cases, a Zener diode is a voltage regulator of choice. That is, it is such a good voltage regulator that almost everywhere we employ this. Now, if you think you have followed the concepts so far, then here are a few questions. We shall try these questions, and not only you will revise those concepts, you will also see many things which we might have missed during these lectures. Example 1, free electrons can move freely between the ions of a metal, yet no current flows through a piece of metal without application of an external electric field. You see, you have a metal wire and there are free electrons in this, but yet there is no current unless you apply electric field. The reason is that the electrons move randomly, the free electrons move randomly, some move this way, some move that way, some move this way, some move this. So, the total number of electrons passing through a cross section is 0, through the net electron flow through a cross section is 0, and therefore, there is no current unless we apply an electric field. So, the motion of electrons is random and there is no net displacement in any direction. When a potential is applied, in addition to random motion, there is a net displacement of electrons which constitutes a current. The maximum number of electrons allowed in a cell of volume h cubed of the phase space is 1, 2, 4, 8. These are the options. Now, let you recall that because of the uncertainty in momentum of amount delta p, uncertainty in the position of amount delta x, delta p times delta x is the size of a cell in which 2 electrons, at most 2 electrons can exist. In 3 dimensions, this cell has a volume h cubed. So, the maximum number of electrons allowed in a cell of volume h cubed in phase space is 2, because not more than 2 electrons can exist, because if the third one will be either upside spin or down spin, which means that it is identical to one of the existing electrons, which is not possible by the exclusion principle. Exclusion principle says that not more than 2 electrons can exist, that no 2 electrons can have identical quantum states. The Fermi-Dirac distribution is given by, I think you remember that this is the distribution given by Fermi-Dirac, and remember that F e is less than or equal to 1 at the most, because if this term is negligible then it is 1, otherwise it is less than 1. And if you differentiate F e with respect to E, it is negative. That means that the probability of occupation of higher states is lower, and ultimately at t equal to 0 there is a step function, and it is 1 if E is less than E f, and it is 0 if E is greater than E f. So, this is the Fermi-Dirac distribution. In the next example, we have the bonds in a semiconductor material are covalent, ionic, metallic, van der Waal, and the answer is covalent. We have seen that the 4 outermost electrons of silicon, they forge covalent bonds with the electrons of the surrounding atoms. The energy gap in EV between a conduction band and the valence band in a semiconductor, we saw that is of the order of 1 EV. For if it is 10 EV, then it is an insulator, and in the conductor they just overlap. The energy gap between conduction band and the valence band, in an insulator is of the order of 10 EV. At absolute 0 temperature, the conductivity of an intrinsic semiconductor is 0, because there is no possibility of electrons breaking these bonds or getting free from these bonds and move if an electric field is applied. So, it is 0 because no electron energy state above the Fermi energy is populated. And in the next lecture, we shall continue with the study of semiconductors, and we shall see the magnitudes of energy gaps in carbon, silicon, germanium, and donor and acceptor energy levels, width of depletion region, frequency of ripples, and so on. We shall see all this.